me again. Now, in this video I want to talk about, I left off in the last case kind of formulating the non-linear system and showing how we took the linear system, okay, a linear system of equations, combined it into sort of one equation, and did the same thing then for a non-linear situation. So if you remember at the end of last video, I started talking about this thing called the hyperbolic functions. That's where I want to pick up again. Okay, and this is something called, the Hartman, Grubman theorem, but it's not theorem, it's theorem 2. So it's a sequel to theorem 1. All right, you can only imagine how exciting theorem 1 would have been. All right, so basically what this says is that we get our eigenvalues out, and providing that the real part is not equal to 0, so these eigenvalues are not equal to 0, then the non-linear case, that means it's hyperbolic, by the way. If the eigenvalues are not equal to 0, the real part of the eigenvalues are not equal to 0, it's called hyperbolic. If they are equal to 0, we have to use a slightly different technique, but we're not going to worry about that for the moment. So if it's hyperbolic, then the non-linear case can be considered just like the linear case, okay, close to the equilibrium point, so xe, okay. So yeah, so basically that's a nice thing because the linear case is really quite straightforward to deal with, or far more straightforward than non-linear case. So basically, providing this condition that when we get the eigenvalues out, that they're not equal to 0, the real part's not equal to 0. Then the non-linear case can be considered just like the linear case, close to the equilibrium point. But now my question is to you, well, what if we don't want to consider things near the equilibrium point? What if we want to consider points away from the equilibrium point? All right. So what we're going to do now is we're going to look at that. This is known as the local. This theorem here is known as the local points, so the points which are local to the equilibrium point. If you like, you go into a village in the middle of nowhere, the locals there are the people that belong to that little area, that little village. Okay, but I want to talk about now the rest of the country, if you like, or the rest of the world, which is the global case. So the case of all the rest of our functions, not just at the equilibrium point, but all over the place, so away from our equilibrium point. Okay, well, let's remember we had dx by dt, and we just set that equal to f. We set that equal to f of xy. And the same for dy by dt. These are two equations that we had, and we called that g of xy. Okay, this is just a reminder of what we had before. So these are non-linear functions, f and g, and we could formulate them into one function. But for the moment, I'm just going to consider them like as they are here. Okay. Right, well, this thing called the solution curves. Okay, now a solution curve, if you remember what we had before, if you go back to my video on phase portraits, what we could basically do is we had y, okay, and y was of y of t, and then we had this up here, which is f of y, and we just said that equal to dy by dt. Okay, if you're not sure on that, go back on what I did. And the solution, so this is like my coordinate plane, which I've got here. My solution is essentially just combined in this plane here, and it is just y against t. So this is t, this is y of t. Okay, and everything which happens in here is my solution. So if you notice that dy by dt, so this is my solution curves. All right, same kind of idea going on here, except now I just want my variables. So my variables are x and y. So notice here my variables were y and t, so everything was in terms of y and t. And what I basically just wanted, my solution curves would lie in the plane of just y and t. So no f of y, no derivatives or anything like that. It's just plain y and t. So likewise here, I just want to define my solution curves in the plane with just x and y. So in other words, I've got this thing going on. So I've got x along here and y up here. And everything which happens in here are known as solution curves. All right, so in other words, my solution curves will be defined by what? The derivative of y divided by the derivative of y over dy by dx. Okay, my derivative of y with respect to x. That's what I'm trying to say there. All right, that kind of makes sense because this is the gradient. Okay, and we're very much dealing with gradients here, except we're looking at how our variables change with respect to time. So how this changed with respect to time, which is dx by dt, and how this changed with respect to time, which is dy by dt. Okay, but of course we could represent that, the solution curves will be represented by the gradients, which is of course just y against x, so it's dy by dx. Okay, hopefully you're following me so far. Now remember, so how are we going to get this dy by dx? I'm just going to make this actually, all this thing a little bit smaller, just so I can fit it in, because I want to very much use these equations which I've got up here. So I'm going to stick this over here for you. You can sort of sit there and ponder about that if you so wish to, if your mind's that inclined. Alright, so basically what I'm after is dy by dx. Well, notice that I've got dx by dt and dy by dt. Okay, so I can use this thing called the chain rule. Remember that I can, although they're not strictly speaking a fraction because they're a rate of change, because of the way that differentiation works, I can just consider it as a fraction. Okay, I mean, I'm not going to go into the proof of all that. Now, if you go back and look at things from first principles and try and look at why that should be the case, why it should be a fraction, you know, and satisfy yourself if you're that way inclined. But like I just say, I'm just for the moment going to treat these as fractions. Well, look, I've got dy by dt. So I've got dy by dt. Okay, it's not quite dy by dx, but I've got the numerator. So what I want on the denominator is a dx. Okay. Well, look, I've got dx by dt. So if I just flip this, I'll have dt by dx. And if I multiply these two things effectively, these two, the dt's are just going to cancel. Right? So I've got dy by dt. Well, what's dy by dt? That's just g. I'm going to drop the dependence on x and y now, because I think that's pretty much given. You follow me, it's just going to take too much time to do. And then dt by dx. Well, look, I've got dx to dt, which is f. So dt by dx, I'm just flipping this. So therefore, I'm going to flip this side as well. So I'm going to have 1 over f. So in other words, I've got now dy by dx is going to be given by my function g over my function f. Okay, and hopefully that makes a little bit of sense to you. Now I'm going to talk very briefly about this thing called singularities, because look, I had up here, I had dx by dt and dy by dt. Remember that I could find an equilibrium point. How do we find the equilibrium point? Well, by setting these two derivatives equal to 0. So dx by dt equal to 0 and dy by dt equal to 0. Okay, so in other words, I'm setting f equal to 0 and g equal to 0, because f is dx by dt and g is dy by dt. So I've now got f equals 0 and g equals 0. So in other words, dy by dx is going to be equal to g, which at the equilibrium point, so at the equilibrium point, this is what I'm considering, I should say that. So at the equilibrium point, which I'm just going to write as at xe, at the equilibrium point, dy by dx is going to be given by these two functions, which are going to be equal to 0. So g is going to be equal to 0, and f is going to be equal to 0. That's 0 over 0. That's undefined. Okay. So at the equilibrium point, the solution curve, because the dy by dx is going to be giving me my solution curve is undefined. Okay. So in other words, I have a singularity, because I can't take the derivative. If I go back to this thing here, I can't take the derivative at an equilibrium point. It doesn't exist. Okay, so that's just something to bear in mind. All right. So now I'm going to talk about sort of what this means. I could go into more detail at this. Basically, what this means is that they solution curves can't cross. So say this is one solution curve. So I've got x against y, x. And I've got a curve in there. Basically, then if I have another curve, they can't cross, okay? And in actual fact, they can meet, but they can't cross. And the only place they can meet is at the equilibrium point, okay? And hopefully you can see that because it's a singularity, it can't actually be at this, it can't actually cross at the equilibrium point, or it's something called a limit cycle. Now, a limit cycle we might come into a little bit later on, but yeah, it's. I'll tell you what it is. So it's basically when you get a closed solution, so something like that. Okay, that's known as a cycle because you can just keep going round and round and round on the same thing. Okay, unlike here where it's sort of a path, you start somewhere and you finish somewhere else. This is a cycle, just keep going round and round. So you've got the cycle bit. Well, hang on a minute. Yeah, so this is a cycle. You're happy that this is a cycle. Maybe if I drew it down here because it's getting a bit messy. So I've got myself a cycle. So I keep going round and round and round. Say if I have an equilibrium point in the middle. Let's just put that in for neatness. And I have a cycle which just keeps going round and round and round. Okay, and that's known as a cycle. Okay, well I can have, say for example, a path which goes into the equilibrium point, to this equilibrium point, so the trajectory which goes into the equilibrium point. This is a stable case. Of course, if it was unstable, then everything would be, the arrows just be the other direction. All right, well a limit cycle is basically where you have a path, a trajectory, which approaches this closed solution. So something like that, okay, and it can also approach from this side as well. So a limit cycle is in the limit, so in other words, as t approaches infinity, so as we go further and further and further and forward in time, we're going to approach these kind of trajectories, and that's known as a limit cycle. So in the limit, we approach these cycles, okay, which is why they're kind of called limit cycles. And this is an example of a stable point because it's approaching the equilibrium point. Okay, so let's go back to kind of where we kind of familiar ground. Let's go back to familiar ground. So we've got dx by dt equals f, and dy by dt equals g. Okay, and I've just said that dy by dx, so the solution curve, can be defined as g over f. Okay, so this is kind of the ideas that we want to now work with and see where we can go with this. Well, basically, if we've got this, so dy by dx equals g over f, we can try and solve that, okay? And we can solve it usually by separation of variables, if we can. But if we can solve it, then we're going to call that, when we solve it, we're going to get the solution, and we're going to call that h, which is going to be called, which is just basically some curve. Okay, this has all come clear in the example, which I'm going to do in a minute. And this is actually going to be given by c, which is our constant of integration. So basically, I'll show you what happens. But essentially, we call this a level curve. Okay, so when we solve this solution curve, okay, we solve this ODE, we're going to get something in terms of x and y. Okay, and we're going to call that a level curve. So a solution curve, level curve, similar kind of thing. I think I'm just going to do it by an example. So for example, say for example if we have dx by dt is going to be given as 4 minus 2y, and we're going to have dy by dt, and that's going to be given as 12 minus 3x squared. Okay, so first things first, we need to get an expression. Let me put that there. Okay, so first things first, we want to get an expression for dy by dx. dy by dx. Well, that's just going to be equal to, if you remember, it's g over f, but I always like to derive it because it doesn't take long anyway. So it's going to be this one. This is going to be giving me this dy by dt multiplied by dt by dx. Okay, so it's going to be 12 minus 3x squared, okay, which is that one, multiplied by the inverse of that one. So it's going to be over 4 minus 2y. Okay, so here's what we've got here. So we've got dy by dx is equal to 12 minus 3x squared over 4 minus 2y. Okay. Well, then if we solve it, now remember we can solve it using separation of variables to get all the y's on one side and all the x's on the other, and then integrate both sides. Okay, so I've got everything involving a y on this side, so I'm going to multiply through. Okay, so I'm going to end up with 4 minus 2y multiplied by dy by dx. Then if I multiply up by dx, to get the dx on that side, I'm going to get 12 minus 3x squared dx. Okay, then if I just integrate both sides, lo and behold, we've just got two integrations, which we can do quite nicely. All right, so this is going to become, what's it going to become? 4y minus y squared. Okay, and this is going to become 12x minus x cubed, and then there's going to be plus a constant of integration, which kind of falls out from both of those, but I'm just going to combine it into one on the right hand side. Okay, so I'm just going to get everything in terms of my solution, my level curve, okay, which is c. So basically just get c on its own. So I'm going to get 4y minus y squared minus 12x plus x cubed. Okay, and this is known, this thing here, that is known as my level curve. So in other words, when I plot this, I will have a solution. Now what I want, so these are all my, this is basically all my curves which happen in sort of my x and y plane. Okay, so my x, y plane is going to be some really complicated function, as you can probably tell. You've got a cubic and you've got a quadratic going on at the same time. So, you know, this is why it's very, very difficult to find things directly sometimes. And this is why, you know, just visualizing what's going on with these kind of trajectories and phase portraits and things like that, you know, really helps, because we don't actually have to, we have solved it, but they can be really complicated functions sometimes. That's basically what I'm trying to say. All right, now we also want to find the equilibrium points. So in other words, where on this function, on this level curve, where on this level curve are the equilibrium points? And remember that the equilibrium points, a bit like the stationary points, are going to be found by setting dx by dt equal to 0, and also going to be found when we set dy by dt equal to 0. So what was dx by dt again? It was 4 minus 2y, and dy by dt was 12 minus 3x squared. So we've got 4 minus 2y equals 0, and we've also got 12 minus 3x squared equals 0. Okay, so let me just try and solve these two things. I'm actually going to move this one up onto the right hand side, so we can have just two nice little columns that we can work with side by side. Don't do that, it's just rude. Come back. There we go. So we're going to have two nice little columns. So let's solve this thing. So we're going to end up with y equals, what's that going to be? Are you happy that that's going to be 2? So y is equal to 2. And I'm going to now solve this thing to find what x equals. So I'm going to end up with, well, I'm going to end up with x squared is equal to 4. So that implies that x equals square root of 4. So that's going to be plus or minus 2. So in other words, my solution curve, my level curve, my equilibrium points on my level curve, so xe, will be given by, it's always going to be 2. Okay, so I'm going to end up with 2 sets of coordinates. So I've got 2 equilibrium points now. So my y coordinate is always going to be 2. My y equilibrium point is always going to be at 2. But my x equilibrium point, one's going to be at plus 2 and one's going to be at negative 2. Okay, so when we plot that, just let me plot that very, very quickly. And then you can kind of hopefully see from the phase portrait exactly what's going on. So just give me a second. Okay, so basically what I've done here is I've drawn my level curve. Okay, I've written out the information again. Let me just change back to, I'm going to stick with this colour actually. So basically I've drawn out my information again. This was what we were given, okay? And then from these we can find the equilibrium points. So I've put my equilibrium points in. These are a bit like my stationary points. So minus 2, 2 and 2, 2. And what I've basically done is I've drawn these level curves in. Now I've had to use a computer to plot them, but we can find the direction of these trajectories just by putting values into here. So we're finding out how x changes with respect to time and how y changes with respect to time. Okay, and then that would give us the trajectories, the direction of trajectories. But yeah, this was basically given by plotting this. Because remember, x and y can take lots of different values. Okay, and if it takes lots of different values, then this is basically what's going to happen. This is what's basically going to look at. So we can actually use a computer to do this. Okay, so what I basically want to do is I want to find out some the direction of some of these. So what I'm going to do is just put in some values. So let's say, for example, let's put in minus 1, 1. So basically I'm looking at that point there. Okay, so I'm going to put in minus 1, 1, minus 1, 1, and I'm going to put that into dx by dt and dy by dt. So remember that dx by dt was equal to, what was it equal to? 4 minus 2y. So that's going to become 4 minus 2 times 1. So 4 minus 2, which is equal to 2, which is obviously greater than 0. So I know that dx by dt is going to be going to the right. Okay, think back to the phase portraits if you're not sure on that, because I'd explain that in quite some detail. Then I've got dy by dt. Well, dy by dt is given by 12 minus 3x squared. Okay, so this is going to become 12 minus 3 times x squared. So minus 1 squared is going to become 1, so it's going to become minus 3. Okay, well 12 minus 3 is obviously going to be greater than 0, so therefore I'm going to be going up. So my y direction is going to be going positively, my x direction is going to be going positively at minus 1, 1. So in other words, I'm going to be going something like this. I'm going to be heading, like, if you like, in a positive direction. So I'm going to go into the left and also up, so I'm going to end up looking something like this. Okay, so I now know that all of my curves are pretty much along this trajectory are going to be doing this. Okay, what's going to be happening over this side? Well, I know what's going to be happening because it's just a circle, right? It's just a cycle, so I'm just going to go around and we're going to do exactly the same thing. It's going to be coming around here. I shouldn't actually have put that line in because here you can see we've got a saddle point. Now I know that this saddle point is going to be going in that direction. Okay, and I'm going to be coming down here. And I'm going to be coming away here. I'm going to be going in there. So just by putting -1, -1 in, I know sort of all this information. So just by looking at the direction of travel, now I'm going to be going round this way. That was I'm going to be going round this way. And then here, because I'm going in that direction, therefore I must be going... Well, I don't know what's going to be happening over here, actually, but I know I'm going to be heading towards the saddle point there. Then if I just trace it back, then this line's also going to be going this way as well. Okay, and also I know that this line's going to be going this way as well because it's on the same trajectory. Okay, so I can fill in this kind of information over here, and it's going to be the same thing over here. I don't know what's going to be happening this side of the equilibrium point, though. Okay, so I do know that those are going that way, and that's going that way, and that's going that way. So I know all this is going on, but I don't know what's happening over here now. So what I'm going to have to do is just put in a value over here, and then, you know, same as we did before, put in a value over here, and just see what's happening. So let's have a look. I'm going to put in, I think I'm going to put in 3, 1. Okay, it doesn't matter, you can choose any value you like, but I'm going to put in 3, 1. So I'm going to look and see what's happening here. So evaluating at 3, 1. I'm going to get dx by dt. Remember, dx by dt was equal to 4 minus 2y. So that's going to become 4 minus 2 times 1. So 4 minus 2. So that's going to be positive. So I know I'm going to be moving to the right. Okay. And actually already now I know the direction of this, but I'm just going to verify by checking dy by dt, just in case something weird happens. So 12 minus 3x squared, so I'm going to end up with 12 minus 3 times 3 squared, so 3 times 9, so that's going to become 27. So that's less than 0, so therefore I'm going to be heading down. So basically if I combine these two, it's a bit like a vector I suppose, you know, I could have combined these two. I'm going to the right and I'm going to up, so I'm going like that and like that. So I'm starting here and going in that direction, so now I know that all my arrows at that point would be heading sort of in that direction. Okay, it's kind of like that, if that makes a little bit of sense to you. So the same thing here, I'm going to be moving to the right, but down. So I'm starting here and I'm going down there like that. So are you happy that that line there is basically just that exact same triangle which I've just drawn there? Okay, so therefore I know the direction of this trajectory is going to be going down like that. Okay, and actually then I know that these trajectories will also be going in the same direction as that. And that kind of makes sense that they're all going down there like that. The next thing is what's happening here. Now I propose that it's going to be going like that because I can just see that these trajectories are going down, so therefore it makes sense that that trajectory is going to be going down as well. You can put in a value as well to verify that. I'm not going to bother because I've got, you know, I know the answer, I did it earlier. I computed it, and this is basically what my trajectory is going to be looking like. So hopefully that makes a little bit of sense. Now, the thing is, you can't really do these without having a computer, which is a little bit unfortunate. But you can do a linear case, and I'm going to do a few examples, or I've done a few examples of the linear case. So it's well worth checking those because they're actually fairly straightforward to do, and then we can look at kind of what's happening with the trajectories and things like that. But yeah, this is basically what's going on. So what do we do? Well, we had our system of linear equations. Okay, from this we can find the equilibrium points and we can put those things on, and then we can get the level curve, and we get the level curve by solving dy by dx. Okay, and just that's going to be equal to, so dy by dx, this is g over f. Okay, and then from that then we can get the level curve just by separating variables or just solving that ODE. Okay, hope that makes a bit of sense.